So one way that we can actually measure these changes in energy, right, how much energy is produced for a certain reaction, is through calorimetry. Calorimetry is a technique that we can use to measure the heat that's involved in a chemical or physical process. So a technique used to measure the amounts of heat involved in a chemical or physical process. Okay. And because we're trying to measure the heat given off by something or the heat absorbed, right, energy transfer between two things, we're going to end up defining a couple of terms that will help us understand what we're looking at. So there's going to be what we call a system, and the system is the substance undergoing the physical or chemical change. Okay, the substance undergoing a physical or chemical change. Now, this might be two chemicals that react, right? A couple of reactants, or it might be some piece of metal that we've heated up, and we want to watch how does it lose energy as it cools down. Okay, it's going to be the thing we're interested in studying. Everything else around it we call the surroundings. Okay. So the surroundings are all other matter. Everything else around the system. And the reason we look at the surroundings is usually the surroundings are involved in the energy change as well, right? If a system is releasing energy, the surroundings will absorb that. Or if a system is absorbing energy, then the surroundings are kind of the reservoir of energy that the system is taking from. So we're going to look at a figure that's going to help us with this. But I wanted to first lay out these definitions, system and surroundings. A calorimeter is the apparatus that will help us study these changes. And this is kind of a fancier one, and this will kind of give us the basics. Like, we'll be able to look at this picture and tell what a calorimeter is used for. So a calorimeter is like this metal container that has a thermometer attached. We're going to end up measuring temperature. Okay. We have some system that we're interested in studying, and again, it can be a chemical reaction or it can be an object of some sort, right? And then everything else around it is the surroundings, even the calorimeter, and even, like the air outside the calorimeter. Okay, so we're going to have a system that either absorbs or releases energy, and then the surroundings around that system. Okay. And so what happens, we've got two figures here where we look at either an exothermic process where energy is released, or an endothermic process where energy is absorbed. And when I say that, I mean energy released from the system, or energy absorbed by the system. Okay. So maybe we have a couple of reactants that react and give off energy. Okay. That energy that's given off is going to go into the surroundings, and usually that's going to be water. So we have some reaction taking place in water around it. The water's going to absorb that energy, and remember, energy is Q. So if our thermometer here is measuring the temperature of the water, right, we can only measure the temperature of the surroundings. As this reaction gives energy off, we're going to see the temperature of the surroundings increase. And it's going to increase, and the amount of energy that it absorbs is directly the amount of energy that's given off by this system. So the Q, the heat, right, the energy released from the system is going to be equal to the energy absorbed by the surroundings. We'll see something similar if we have an endothermic reaction. So if we have an endothermic process, what that means is energy is being absorbed into the system, right? The system is taking energy from its surroundings. Again, labeled Q, that's energy. It's going into the system, and what that means is if the system is taking energy from the surroundings, then the surroundings will have a lower energy, and you're going to see the temperature decrease as energy is lost by that solution, by the surroundings. Okay, so if energy is absorbed into the system, it's being taken from the solution, the surroundings here, and temperature decreases. But what we can see is the amount of energy that's taken from the surroundings is going to be exactly equal to the amount of energy that was required or absorbed by the system. So the energy absorbed by the system is going to be equal to the energy taken from surroundings. Okay, so at this point, I want you to see what a calorimeter kind of is. It's some structure that mainly is just trying to isolate this system and prevent as much energy transfer out into the rest of the atmosphere that we can. We can't measure anything out here. If we can isolate all of this and have our own system and surroundings, then we can actually measure the temperature changes and it means something, right? We can get some accurate results. So we need some way to isolate and prevent heat transfer out into the rest of the world. So we have some structure here. We have to have a thermometer that's going to end up measuring the heat transfer, right? We're going to end up taking measurements that are in temperature units, right, degrees Celsius. And then you need some system you want to observe and then some surroundings around it. Okay? The other thing that I want you to take from this is that there's some amount of energy involved. There's always going to be an energy transfer, and the amount that the system loses or gains is going to be exactly the amount that the solution gains or loses. So if I start to consider this mathematically, what this is going to mean is that the energy change that we see in the system plus the energy change that we see in the surroundings, as long as this is happening in a calorimeter, we say that that's equal to 0. And what this 0 means is that there's no energy lost beyond the walls of the calorimeter. Or no energy lost even into the walls of the calorimeter, right? We're trying to say that any energy that's transferred from the system goes into the solution, okay? Or any energy that goes into the system comes from the solution or the surroundings, and we can measure that with a thermometer. So here we're just saying the energy change of the system and the energy change of the surroundings should exactly balance out so that no energy is lost, and we can actually determine how much energy the system has either gained or lost. So if I rearrange this, what I'm going to see is the energy change for the system is going to be equal to the energy change of the surroundings. That's going to mean it's the same number, the same amount of energy, surroundings, but we're going to have a negative sign here that means that the direction of the flow of energy is the opposite. Okay, so what that means is if the system loses energy, like in an exothermic reaction, then the surroundings are going to gain. That's what this negative sign means, the direction, right? If the system loses it, the surroundings gain it. If the system gains energy in an endothermic reaction, then the surroundings are going to lose that amount of energy. So the sign just tells us the direction that the energy is flowing. And it's going to be the opposite of whatever we see in the system energy change. I know this can be a little bit confusing, so I want you to try to absorb what the concept is saying, and then we're going to apply some math. But all it's saying, right, is if the system loses energy, the surroundings gain it, or in a different process, if the system gains energy, then the surroundings are going to lose that same exact amount of energy. Let's look at this in the context of if we drop some hot metal, so M is metal, if we have this metal that we heated up and we drop it into cold water, water is W, and the metal gives energy off as it starts to cool down. What we can say is, right, we have hot metal that we dropped into cold water. Initially, we're going to see energy given off by the metal, Q metal. There's some amount of energy that is given off, and that's going to go directly to the water. The metal is losing energy because it's cooling down, and the water is gaining energy as it heats up, right? The metal, as it cools down, is transferring its energy to the water until we reach some thermal equilibrium here where the metal and the water are the exact same temperature. Okay? So we're going to see this heat transfer or energy transfer until both the water and the metal, both the system and the surroundings, reach the same temperature. And we see we have some initial temperature of the water here, and then we've got a final temperature here. This temperature difference is going to ultimately tell us how much energy did that metal lose. Okay. So I'm going to stop the video at this point, but we're going to do some examples where we look at calorimetry and how can we use calorimetry to actually determine a number for the energy that's been transferred. So I will see you guys then.